Now, every matrix is, of course, special in its own way, but we're going to talk about some special properties of matrices in this segment, and they are basically attributes that a matrix might or might not have, and it turns out to be useful to know if it has one or more of these properties because some special rules apply. So the first one is pretty easy. In fact, these are all fairly easy except for maybe one or two, and that's the notion of a square matrix. And a square matrix is just one where the number of rows is the same as the number of columns. So this matrix right here is not square because it's got 2 rows and 3 columns, whereas this matrix is square. Got the same number of rows and columns. Easy peasy. Next one, a symmetric matrix is one where the rows and the columns are interchangeable, meaning you get the same matrix if you do that. Another way to look at it is if you have a matrix I. If Aij is always the same as Aji, then it is symmetric. So let's look at an example here. Here's a matrix 4, 9, 2, 9, 3, 7, 2, 7, 1. If you look at that matrix, you will discover that it does in fact have this property. A11 is of course equal to A11, that's 4, duh, that's of course always going to be true on the diagonal here. And by the way, this is called the diagonal of the matrix. I can't remember if I've mentioned that or not, but the diagonal goes from the upper left to the bottom right, and that comes up a lot. It's also true that A12 equals A21, right? Those are both equal to 9. And A13 is equal to A31. Those are both equal to 2. And finally, A23, the other interesting one, is equal to A32. They're both equal to 7. So the way I think of it is, if you have your diagonal here and you kind of draw a line through it, symmetric means it's like a mirror across the diagonal. So the 9 and the 9 match, the 2 and the 2 match, the 7 and the 7 match. So it's symmetric along that axis. That's very important. It doesn't matter if it's symmetric, along that axis. There's no special name for that. Or if it's symmetric along this axis, there's no special name for that. Or if it's symmetric along this axis, there's no special name for that. The only one that really matters is the diagonal, and if it's symmetric across the diagonal, which basically boils down to whether or not that is true. And that turns out to be extremely important for us. All right, next one. We're going to call a matrix upper triangular. Now you might be thinking, wow, triangular? How do I make a triangle matrix? Well, a matrix is, of course, not triangular, it's rectangular. But this matrix is upper triangular because all of the elements below the diagonal are 0. So the only thing that really has any substance to it here is the diagonal and the things above the diagonal. So that, red square or red triangle there is a triangle shape, right? And all those in the red are the only ones allowed to be non-zero. So everything below the diagonal, sometimes people will call this the main diagonal. I'm just going to call it the diagonal to save myself some writing. Everything below the diagonal is 0. By the way, you notice that it's possible to have something 0 up here. It's possible to have something 0 on the diagonal. Those don't mess up the upper triangularness. But the upper triangularness just means that anything not in the red triangle here is going to be 0. And there's also another similar term called lower triangular, and you can guess what that means, right? Lower triangular means everything not in the blue triangle is going to be 0. So that one doesn't come up first quite as much as upper triangular does, but it's sort of a symmetric relation there. By the way, we're going to say that if you're going to be symmetric, that implies that you are square. We're going to say that there's no such thing as a symmetric matrix that's not square. And the same thing is also true for upper and lower triangular. If you're an upper triangular matrix, you've got to be square. Don't even be trying to convince me that you're an upper triangular if you're not even square. Okay, those things both apply. And the same thing is also going to be true for a diagonal matrix. We're going to say all diagonal matrices for our purposes are square. And a diagonal matrix is simply one where it's all zeros not on the diagonal. So we can have 4, 3, 0, 2. And then all zeros up here, and all zeros here. That's a 0. That is a diagonal matrix. In a diagonal matrix, the only thing that's allowed to be not 0 is the diagonal itself. And of course, we can have zeros on the diagonal, but the important thing about a diagonal matrix is everything not on the diagonal must be 0. And of course, you also must be squared to be diagonal. All right? Now, even more limiting, so to speak, is the notion of an identity matrix, and we'll see why it has that name in a couple episodes. There's a very deep reason it has this name. But an identity matrix just means zeros everywhere except the diagonal. So far, it's the same as a diagonal matrix. But we're going to insist that an identity matrix has ones on the diagonal. It must only be 1. Nothing else is allowed. So that's a pretty restrictive constraint, as you can see. Here's an identity matrix. 1, 1, 1, 1, and then zeros everywhere else. Sometimes I'll draw it like this. I'll just draw a big 0, indicating that everything down here below the diagonal is a 0. And of course, we could have a smaller one. This is an identity matrix. And you can have one as large as you want, right? But for any particular size, there is only one identity matrix because we basically constrain it to be exactly this here, right? All right, so that's identity. And then the hardest one, maybe, and it's not that hard, but you just kind of got to squint at it, is the notion of a block diagonal matrix. So we know a block diagonal matrix has zeros except for the diagonal. So here's what a block diagonal matrix is. Suppose I have a matrix that looks like this. 3, 2, 9, 0, 0, 0, 4, 1, 6, 0, 0, 0, 2, 5, 7, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 3, 2, 5, 0, 0, 0, 9, 7, 17. Right? Now, clearly, this is not a diagonal matrix because we've got all sorts of things here that are not on the diagonal that are nevertheless not 0. So it's clearly not diagonal. However, we're going to say this is block diagonal. And here's what we mean by that. We mean we can partition the matrix like this. And there's a number of applications where you partition a matrix into chunks. And what we're going to say is that if it's block diagonal, that means you can partition it into chunks. And each of the chunks on the diagonal must be square. So this thing right here, which is on the diagonal of the chunks, must be square, as does this one have to be. Okay, the ones off diagonal do not have to be square, but the ones on the diagonal have to be square. And everything over here is 0, and everything over here is 0. So we're basically saying that the matrices not on the diagonal of this big matrix are 0. Can you see that? So it's kind of a weird way to define the diagonal because we're essentially defining the diagonal to be this block and this block. And we're saying if you're not one of the diagonal blocks, then you must be all zeros. And it turns out that it's going to be useful sometimes for us to say, hey, if we have a matrix that can be partitioned in a way that it's block diagonal, there's certain truths about that. It's especially true we're going to look at when we apply it to graphs and social networks, when we represent a social network as a graph and talk about its so-called adjacency matrix. Then if that adjacency matrix turns out to be block diagonal, it has certain properties of the graph that implies. So we'll get there a little bit later. All right, let's do some quick review, make sure we understand all this stuff. Here's a matrix. What are its dimensions? What by what? Pause the video and figure out the answer, then resume it to see if you're right. And the answer is this is a 2 by 4 matrix, not a 4 by 2. We always list the number of rows first and then the number of columns. This thing has 2 rows and 4 columns. How many rows does this matrix have, and what is the dimension of each of the rows? Answer, this has 3 rows, each of which is a 2-dimensional vector. 1, 2, 2, 3, and 3, 9 are the 3 2-dimensional rows. How many columns does it have, and what's the dimension of each column? It has two columns, each of which is 3 dimensions. So there's 2 different ways to think about this matrix. You can think of it as a set of 3 2-dimensional row vectors, or as a set of 2 3-dimensional column vectors. Here's Q. What's Q transpose? Remember, transpose means we interchange the rows and the columns. So the rows become the columns become a row. Easiest way to do that, I think, is to say, well, let's take the first row, and that first row, let's just write that as a column. So instead of 2, -7, -4, 1, 2, we're going to write it as 2, -7, -4, 1, 2 as a column. And then we're going to say, take the second row and make that be the second column, and then the third row and make that be the third column. Next, what is the sum of these 2 matrices? Answer, cannot do that. You cannot add matrices unless they are the same dimensions. These are not. What if we make them the same dimensions? Now, what is the addition of these 2 matrices? Here we get 9, 3, 10, 5, 11, 12, because matrix addition is a very simple operation. It just means add each of the respective elements. So 1 plus 8 is 9. That's why the upper left corner is 9. 2 plus 1 is 3. That's why the upper right corner is 3, etc. Let's do some scalar multiplication times vectors and then addition. What happens if I get 4 times that first matrix plus 2 times that second matrix? What do I get? If you work that out, you should get that answer at the bottom, because scalar multiplication is nothing more than multiplying each of the elements by it. So we're going to multiply 1, 2, 2, 3, each of those by 4. And then we're going to multiply each of these elements by 2. And then we're going to add up the respective elements. You ought to get that. What if I transpose the first guy? Then what do I get for my answer here? Turns out the same thing, and that's because this first matrix was symmetric, right? 1, 3, 2, 2. It turns out that since the 2 here is equal to the 2 there, this matrix is symmetric. Therefore, taking the transpose doesn't change it. And therefore, the answer I get to this entire operation doesn't change. But if I take the transpose of both of them, what do I get? Now I do get a change. In fact, it flips the order of the answers here. In fact, gives us the transpose of our original answer, because now the 9 and the 2 are flipped before I do that scalar multiplication there. All right, what do I do if I get this matrix times this vector? What do I get? Again, no can do that. Es imposible, because we are not able to multiply a matrix times a vector unless the number of columns is the same as the size of the vector here. Let me do it this way then. Let me give a 3 by 1 vector that we're multiplying this by. Do weigh 1, so think of this as the dot product of the vector with all the rows, and compute the answer. What do you get? You should have gotten this, 25, 9, 13, 11. And that's because we take each row, like 4, 1, 6, and dot product that with 3, 1, 2. So 4, 1, 6 dotted with 3, 1, 2 gives you 25. 2, 3, 0 dot producted with 3, 1, 2 gives you 9. All the way down, you end up getting that answer there. Now, compute the same thing using way number 2. So think of this as a linear combination of the columns. We want 3 of the first column, 1 of the second column, 2 of the third column. What do we get when we get it that way? Obviously, the answer should be the same, and you should verify that you get that when you're thinking of it as 3 of this domino, or I guess quadromino, 1 of this quadromino, and 2 of this quadromino. All right, now about our special matrices. This guy right here, A, is he square? No, he's not, because he has more rows than columns. What about B? Is he square? Yes, indeed. Same number of rows and columns. C. Is C upper triangular? No, it's not, because remember, the thing that matters is this triangle up here. The main diagonal goes from upper left to bottom right. That's the only diagonal that matters. And when we say upper triangular, we mean everything below that is 0. Here we've got these 3 elements 0, but that's not what matters. That's not what counts. That's not what makes it upper triangular. Let's swap that around. Is D upper triangular now? And the answer is yes. Is E upper triangular? And the answer is yes, because all of the elements, all 3 of them below the main diagonal, are indeed 0. And remember, that's all that matters. The other ones could be 0 too. No skin off my nose. The only thing that's required to be upper triangular is that the ones below the main diagonal are 0 as they are. Is E a diagonal matrix? Yes, indeed it is, because everything off the diagonal is 0. As it happens, everything on the diagonal is also 0, but that's immaterial. Is F a diagonal matrix? Yes, it is, because, of course, the things that are off the diagonal are 0. Now we have the things on the diagonal being non-zero, but that's totally kosher. Is F an identity matrix? No, because everything on the diagonal would have to be 1s for it to be an identity matrix. G, is that an identity matrix? Again, no, because we've got a -1 lurking down there. What we're going to have to do is put all 1s on the diagonal. What about this guy, H? Is he an identity matrix? We're going to say no, because you got to be square to be an identity matrix, right? It doesn't really make sense to talk about a matrix that's not square being an identity. What's I? Is this guy an identity matrix? Yes, it is. And by the way, I is going to be the symbol that we normally use for the identity matrix. Normally we'll say I, and maybe we'll say I sub 5 if we want to specify that it's a 5 by 5 identity matrix. But that's going to end up being the letter that we use when we're talking about identity. Is I symmetric? Yes, it is, because row 1, column 2 is the same as row 2, column 1. Row 1, column 3 is the same as row 3, column 1. All diagonal matrices are going to be symmetric. What about this guy? Is J symmetric? No, it's not, because even though you can draw a line from upper right to lower left and say that it reflects across that, again, that's not what matters. What matters is the upper left to bottom right diagonal, and it is not symmetric across there. Row 1, column 2 is 4, but row 2, column 1 is 3, therefore this does not meet the requirements for symmetry. What about this guy, K? Is he symmetric? Again, no, same problem. We do not have the case that the rows and the columns are interchangeable. What about L? Is L symmetric? Yes, finally we have one, because now it's true that for every row I, column J, the element at row J, column I is the same. Is L a block diagonal matrix? No, it's not, because you can't partition it into blocks. What about this one? Is M block diagonal? Yes, it is, because we can take this upper thing of 9, and that is the upper left block, and then the lower right block is just this single element 7, and everything not in one of those diagonal blocks is 0. So you can think about it as partitioning with a line right there and a line right there. And we do in fact have a square guy up here, a square guy down here. Everything not in one of those blocks is a 0. What about N? Is N block diagonal? We're going to say no, it's not, because the diagonal blocks have to be square. So even though you can kind of eyeball this and say, well, gosh, if I drew a line right here and then drew a line right here, well, then I would partition it into rectangular thingies, and the off-diagonal rectangular thingies are all 0. Yeah, true, nice try. But we're going to say that the non-zero diagonal blocks have to be square, and here you have to do a rectangle one. Notice there's no way to partition this so that you have square diagonal matrices, square diagonal blocks, and all the ones off it are non-zero, right? If you divided it here and here, then you'd end up having this 7, which is, or excuse me, if you divided it here and here, right, you'd have this thing which is supposed to be 0 and is not. And if you try to divide it here and here to get a 3 by 3 up here, then your 1, 9, 3 would all be jacked because they are non-zero and not in one of the diagonal blocks. Finally, what about O? Is O block diagonal? And we're going to say yes, because we can, in fact, partition it into a 4 by 4 in the upper left and a 2 by 2 in the bottom right. Everything not in one of those diagonal blocks happens to be 0. There you go.